So today we're going to look at current electricity, right? We've looked at static charge, how electric fields form, and the concept of electric potential, and what a basic circuit looks like. So now we're going to understand how a charge can flow through that circuit. So here are our objectives. Describe conditions that create current in an electric circuit. Understand what determines electrical resistance. Explain Ohm's law. And then differentiate between power and energy in an electric circuit. And then we'll look at some examples using Ohm's law to determine the current and voltage in a circuit. All right, electric potential difference, right? Little review here. Electric potential difference is the equivalent to the work done on a charge or electron to increase its energy, right? And we know the units for that is a volt. Now, let's take that concept. Let's look at these plates on the right here, parallel plates. They're conductors. And the top plate has a positive charge, the bottom plate has a negative charge. So we know that electric field, right, would be set up between those two plates. And that the charge, if there's positive charges on the top plate, those positive charges would want to move from a high potential to a low potential, right? So if we put our arbitrarily small test charge here, positive, it would move down to the lower plate. Okay. Now, if we provided a easy path, right, a conductor where the charge can move freely between the high potential plate and the low potential plate, right, all those positive charges would travel from high potential to low potential through that conductor, and over time. Actually, it wouldn't take much time at all, but over time, right, all of the positive charges would move to the low potential plate and combine with the negative charges, and basically we'd have a neutral charged object, right, equal number of positive and negative charges. And we could measure the amount of a charge flowing, right, from the high plate to the low plate through that conductor. So the flow of charge stops when the electric potential is zero. Now, let's look at an analogy with water and pressure, okay? You can see a reservoir to the left that is filled almost to the top, so there's high pressure there, right? And then it goes through a gate, a valve at the bottom here into the other chamber, and you can see that would have lower pressure, right? Because it's not as full of water. So if we let that water flow, right, the pressures will equalize, right, between those two chambers. And then once they're equal, the water stops flowing. Okay, so the flow of water we could measure in terms of gallons per second. Okay, so the analogy here is between the water is like the current, right, flowing, and the flow is determined by the pressure differential or the differential in electric potential. Okay, and we call that flow of charged particles current or electric current. Now let's take this one step further here. Okay, what if we added a battery to our system here of charged plates? And the battery's job, remember, is to raise the electric potential of the charges. So the charge would lose potential energy as it flowed through the conductor, but then the battery, right, is going to increase the potential energy of that charge, right, by boosting it from its negative to its positive terminal back up to the high potential plate. Right? So you would get a flow of charge that travels in a circuit, right, through the conductor and then back up through the battery. And the charge would just continue to cycle through as long as we have energy available in the battery to do that work, right? Most batteries are chemical batteries. So once that chemical energy is used up, then it no longer would be able to increase the electric potential or electric energy of the charged particles. Same thing holds true for our water analogy here, water pressure analogy, right? If we just left the water to equalize in pressure, right, it would do that. But what if we added a pump at the bottom? The pump is similar to the battery, right, to take the water in the low pressure side and pump it back up to the high pressure side and maintain that high pressure differential. So the pump here is raising the water pressure, or think of it as potential. So here's the another analogy, right, between electrical current and the role of a battery, and water current and the role of a pump. So let's talk a little bit more about batteries, right? Here's a common D cell, right, that we are all familiar with. It supplies the energy in a circuit. It pumps the charge from the negative terminal to the positive terminal, and it maintains an electric potential difference across the external circuit, right? These types of, we call these dry cell batteries, D size, C size, AA, AAA, they all have a electric potential difference of about 1.5 volts. And if we connect them into a circuit, right, we have what we call the internal circuit. That's where the charge is being increased in its potential by the battery. And then we have the external circuit where energy is lost as the charge does work, in this case, lighting up the light bulb. And we can map out the change in potential that the charge sees as it moves through the circuit, right? We have the maximum potential at 1.5 at point A, positive terminal of the battery, and also at point B, assuming we have a good conductor, right, that can easily move the charges. So as we travel around the circuit, right, we lose that potential energy. So from 1.5 to 0 as we go through the light bulb, and then C and D will be at the same potential with a good conductor connecting the two of them. So let's formally define electric current. It's the rate at which charge flows through a circuit. Okay, so we can calculate current, I, as the change in the amount of charge that flows through a given point in the circuit divided by the time period. Okay, so it's the rate at which charge flows. The unit we have for that is called an ampere, and we use a capital A as an abbreviation for that unit. So 1 ampere would equal 1 coulomb of charge per second flowing past any particular point in the circuit. So here's an example, right? If we had 20 coulombs of charge flowing through our circuit at any point, we'll talk about measurement here in a second, and we did that for 5 seconds, then the current flow would be 4 amperes. Now, to measure current, a meter, we call it an ammeter, must be inserted into the circuit because the current has to flow through the meter. So the ammeter actually becomes a part of the circuit. Now, a good ammeter won't use any energy in the charge as it flows through it. It's able to measure the amount of charge, but not reduce the electric potentials. But it does have to be inserted into the path that the charge is going to flow through. Now, one other comment here, the same amount of current flows through every element of the circuit. So that 4 amps flows through the battery. It's the same 4 amps that flows through the ammeter. It's the same 4 amps that flow through the light bulb, right? The current is going to be the same anywhere along that loop or circuit that it flows. Now, everything we've talked about so far kind of assumes that we have positive charges that are flowing. Okay, and we call this conventional current, okay, because it just makes sense in terms of our model of how a positive charge reacts in flowing from a high potential to a low potential. Now, the reality we know is that positive charges, protons, are very hard to free up and move through materials, but even good conductors. So the reality is it's the electrons that are flowing through a circuit. and they would flow in the opposite direction, right? Since it's a negative charge, they're going to flow from the positive or negative terminal of the battery through the circuit and then back into the positive. Okay? So we think about it in terms of positive charge, but in reality, it's really electrons, negative charges that are flowing in the opposite direction through this circuit. All right, let's talk a little more about voltage sources. We got chemically based, right? Different types of batteries. We talked about the dry cell, a wet cell battery like you use in your car. Another type is what we call a fuel cell. And this is where electricity is generated by a chemical reaction between hydrogen and oxygen. And this was once a pretty promising technology to use in cars that could generate electricity or generate hydrogen and oxygen that can be used to run the car, to burn in the car. Electric battery technology has advanced greatly in the last decade here, and you don't hear as much about fuel cells anymore. Generators, right? Mechanical-based voltage sources. This is what a generator or alternator looks like on your car, right? The fan belt turns it, and it produces an electric potential or voltage source for your car to run off of. Here's a power generator, right? These are becoming more common as people deal with the power outages we have during fire season. On a very large scale, right, we have these huge generators that are driven by a turbine where water flows through at the base of a dam and spins the generator, and that produces electrical potential. If you look at that picture, you can see the stairway going up to the balcony there, and you can get a feel for the size and scale of these generators, just massive. And then, of course, wind energy is used to turn the generators, and we're seeing more and more solar, right? Solar is actually playing a pretty large part of our energy source here in California, especially out here in the West. Now, the last concept we're going to talk about is electric resistance. Okay, so if you looked at this tank of water with two pipes coming out of it, which outlet would allow the greatest flow of water? Well, the larger the diameter, right, of the outlet, the easier it is for the water to flow out. So even though each of those outlets is going to see the same pressure, the larger tube has less resistance to the flow of water. It's going to allow more current or more water to flow out of it. Now, the same concept can be applied to circuits. A common element that's in electrical circuits is a resistor, or something that provides resistance to the flow of current. If you don't have any resistance in it, the current is going to flow at a very high rate out of the battery. Matter of fact, it can actually cause the battery to damage itself or even explode. So often we have resistance in the circuit that controls the amount of current that flows. And really, we're controlling the amount of energy that's being used by the battery. So once we close the switch, right, the circuit is complete and the current can flow through the resistor, through the switch, and then back through the battery. Now, the resistance of a conductor depends on several things. The resistivity of the wire, this is the property of the material itself, and the higher the resistivity, the greater the resistance to a charge flowing through that. The thickness of the wire, just like the larger pipe coming out of our tank of water, the thicker the resistance, or the wire rather, the lower the resistance. And then the length. The longer the length, the more resistance it's going to have. The shorter the length, the lower resistance. Resistance is measured in ohms, and it has this funny little Greek symbol for omega, O, Greek large capital letter O. But the unit of measure we use for resistance is an ohm, OHMS. So let's look at a circuit here. We have one connected with a copper rod and another connected with a glass rod. Right? So which one's going to have the greatest current? Well, the one with the copper, because copper has much lower resistance. its resistivity is much lower than that of glass. Glass is actually a pretty good insulator and in most cases won't allow any charge to flow through it. Okay. All right, so if we look at the math behind resistance, the symbol R for resistance with the units of ohms, we can calculate the resistance by the voltage across the resistor divided by the current flowing through it. Okay, so the resistance is the ratio of the voltage divided by the current. This is known as Ohm's law. So let's look at some examples here. We'll ignore the first circuit here, but it just shows the resistor, right, across the battery terminals, and the current's going to flow through that circuit. So using Ohm's law, can we determine how much current is going to flow in these circuits? So the middle one, notice we have 3 volts divided by 30 ohms. That's going to give us the current. Now, notice I've rearranged the equation, right? It's the same 3 variables, current, voltage, and resistance, but in this case, I rearranged it to solve for current, right? We can use Ohm's law to solve for any one of the 3, current, resistance, or voltage. Now let's look at the bottom example here on the right, right? It has a 6-volt battery with a 60 ohm resistor, but if we solve for the current, we see it would actually have the same current flow, 0.1 amps. Right, let's talk a little bit more about factors that determine resistance. There's actually a formula for that. You see in the center here, R, resistance, is equal to, and this first parameter here is the Greek letter rho, small letter rho. Rho, if you look at the bottom, is the resistivity of the material. Okay, so this is just the property of whether it's a good conductor or a good insulator, then times the length, and then divided by the area. So this just fits what we talked about, right? The resistance is going to be directly proportional to the resistivity and the length, and it's going to be inversely proportional to the area. So the greater the cross-sectional area of our conductor, the lower the resistance. Here's another way to think about Ohm's law, right? Kind of have this cartoon here, right? Voltage is the pressure that's trying to push the current right through the pipe, and the resistance, the ohms, is what's restricting the flow of that current. Now, this is a little triangle that helps us to remember Ohm's law, right? The V in the top and then the I and the R. So whichever parameter you're calculating, you cover that up, and then the other 2 parameters, it gives you kind of the formula for that, right? So if we covered up the voltage, voltage is equal to I times R. If we covered up the I, we're solving for current, what would be left? Voltage over resistance. If we solve for resistance, right, what would be left? Voltage over current. All right, power. Power supplied or consumed by a circuit element is equal to the current times the voltage. So the current flowing through the element. So let's say we're trying to figure out how much power a battery is supplying. We would say, what is the current flowing through the battery? And what is the electric potential difference across the battery? And we just simply multiply those together, and we get power in the unit of watts. Remember, we talked about power back in the first semester. So it applies as well to electrical circuits. Now, power, remember, is equal to the work done on the charge divided by the time, right? Work done is the same as energy. So we can also calculate the energy that is being used by a circuit by simply taking the power and multiplying that by the time period. And that will give us the total amount of energy used by a circuit. Remember, power is just at any instant in time how much power is being used. Energy in an electric circuit depends on the power and the amount of time that the circuit is running. All right, let's look at one last example here. So we have a 6-volt battery delivering 0.5 amps current to an electrical motor connected across its terminal. So let's draw a little circuit that shows those connections. Okay, here's our motor, Here's our battery. We put an ammeter in there, right? So we can measure that current of 0.5 amps. Now, what power is delivered to the motor? Well, remember, power is just current times voltage. So the voltage across the battery is the same voltage drop across the motor. So there, we would use 6 volts times the 0.5 amps, and we would get 3 watts. We would say the battery is providing 3 watts of power, and the motor is using that 3 watts of power. Now, to find the energy, it says if we ran the motor for 5 minutes, how much energy would be used? Well, remember, the original definition was the power times the time, and the time is going to be in seconds. So we need to convert that 5 minutes to seconds by multiplying it by 60. So we have 3 watts times 5 minutes times 60, and we get a total of 9 times 10 to the second, or about 900 joules. Another way to describe the power would be watt seconds, right? Because we had 3 watts for 300 seconds, and that gave us 900 joules or watt seconds. All right, that's it. So we know how to describe the conditions that create a current in an electric circuit. We can explain Ohm's law, and we know the difference between power and energy in an electric circuit. Okay, that's it.